This is a lecture for statistics on Chapter 4, and this is a lecture on combinatorics. It's a little different from probabilities. Also, the notation is a little different because now P will mean the number of permutations, not the probability. Calculating these combinations and permutations involves a new operation called factorials, and that's what's shown here. Factorial is shown with an exclamation mark. And what it means is to take the number that you're working with and count down, multiplying as you go. 5 times 4 times 3 times 2 times 1. Stop at 1. And then you just multiply that up. 5 times 4 is 20. 20 times 6 is 120. That's the answer. Doesn't matter what number you start with, as long as it's greater than or equal to 0. You don't use factorials on negative numbers. So if you had 10 factorial, you'd just be 10 times 9 times 8 times 7 times 6. And you go all the way down, times 4 times 3 times 2 times 1. But you don't multiply by 0. The answer would be 0, of course. That's interesting. You don't multiply by 0 because you can take 0 factorial. I'll show you how that works in a minute. Let's try this fraction, the second example here. Now with the factorials, you can abbreviate. All this from here to here is 3 factorial. So I could have written this as 5 times 4 times 3 factorial. See? And there's a reason why that is a good idea. Let me clear the screen for a minute, and then I'm going to do the second problem. Okay. In this problem, I could write this out. Well, that's too much work, so I'll write out a smaller problem. Say I had 5 factorial over 3 factorial. I could write 5 times 4 times 3 times 2 times 1, and this is 3 times 2 times 1. And then I could just cancel the 3's, cancel the 2, cancel the 1. There's my answer of 20. Instead of doing that, I could count down to where I have a 3 factorial in the numerator. I've got the 3 factorial in the denominator. And then I cancel all those at once. Remember, canceling turns things into 1. And then the answer is the same, 20. When I have a small numbers like this, 5 and 3, I could do it this way, or I could do it this way. But when you get bigger numbers, it becomes very hard to do it the long way. Instead, you want to do it this shorter way. So I'll do this one up here. So I can go down 15, 14, 13, 12 factorial. Here's 12 factorial. I just cross those out, and now I just 15 times 14 times 13 is the answer. Because it can be abbreviated this way, we actually can get a value for 0 factorial. Because this is just not algebra, I won't give you the proof, but 0 factorial is equal to 1. 0 and 1 are weird numbers. They look like they're real simple, but what do they say? Deep waters, still waters run deep. They're sort of like that. They just 0 and 1. In fact, with 0 and 1 and Peano's axioms, you can construct all the other numbers, all the real numbers. So they're pretty good numbers, but they behave sort of strangely sometimes. And 0 factorial is equal to 1. So if I had something like this, 3 factorial over 0 factorial, if you had it just over 0, you'd say undefined because you can't divide by 0, but in this case, this is the same as 3 factorial over 1, which is 3 times 2 times 1 over 1, which is just 6. In this lecture, we're looking at computing the total number of either combinations or permutations. This is not about probability, although it could kind of play into probability. We're just going to look at counting them up, and there's certain rules for them. Now, permutation are groups in which order is important. For example, if you had people up to bat, I guess it would count who you put first, second, third, and fourth. If you have a committee, these are just the committee members. Often you write them in alphabetical order for no good reason, because there is no member the fact that he's first member and that she's second member, that doesn't have any meaning. They're just all committee members. That's a combination. Permutation are arrangements where order is important. Combinations are arrangements where order is not important. So the big difference here is the word order. If you have a group of objects, like say five books, and you want to arrange them on a shelf, and you want to say, what are all the different arrangements I can have of these on the shelf? These would be your permutations of them, because order would be important. We're going to say, if I have Robinson Crusoe first, that's one arrangement. If I have Robinson Crusoe second, that's another arrangement. Okay, so order does count. And so we're talking about permutations here. Well, when I go to put the first book on the shelf, I have a choice of 5 books to put up there. All right. Now, for the second place, I only have 4 books left to put up there. Then for the next place, there's only 3 books in the box to put up there. Then I've got 2 books, and then the last one, of course, is just 1. When I multiply all these out together, that gives me the total number of permutations in the box. And so that is, in this case, it's 5 factorial, right? And we write that as a permutation of 5 objects taken 5 at a time. This is for the size of the arrangement. This is for the total number of objects. Now, if you don't take them, if you're not taking those 5 books that are in the box and putting them all on the shelf, say maybe you're putting arrangements of 3 of them, well, there are always going to be 2 books in the box that didn't make it to the shelf, and that's going to decrease the number of permutations that you have. So you account for that by dividing like this. If you have n objects and you use all n of them to make your arrangements and permutation, order counts, it's n factorial is the answer for the number of permutations that you can have. If you take them r at a time, for example, you have 5 books but you take them 3 at a time, it's n factorial, but you divide out n minus r factorial, the number that don't make it into the arrangement. So here is the equation right here. This one reduces to this equation because when r is equal to n, then I have n factorial over n minus n factorial. N minus n factorial is 0 factorial. But remember, 0 factorial was 1, so this is just n factorial, which is what we get up here. Now, if you have combinations, you'll have fewer combinations because things that look different on a permutation actually aren't any different when it comes to a combination. Just like if you wrote all the members of the committee in alphabetical order descending, or if you wrote it in ascending alphabetical order, you still have the same committee and there'd be no difference. So while those would be 2 different permutations, they are the same combination. So you'll have the same type of arrangements, but you're going to have fewer of them. And we use the same notation, number of combinations of n objects taken r at a time, n factorial, then we have the n minus r factorial. So at this point, it's the same as the permutation, but then you divide by r factorial because that gets rid for you of those duplicates. So here are the formulas. I just want you to be able to write the formulas down. There are buttons on the calculators for calculating these formulas. You can't use it on the test. You have to be able to write it out. So although it's good to check your work, I think you need to be able to write down these equations and substitute into them properly, and then use your calculator. So we're going to apply the formulas here. We have 3 objects, x, y, z, and we want to take them, we want to calculate the permutations and the combinations for taking these 3 letters, taking them 2 at a time. That means making arrangements, x, y, x, z, y, z, etc. So the formula for permutations, these are the ones where order does count. Order makes a different arrangement. N objects taken r at a time is n factorial over n minus r factorial. In this case, we have 3 objects taken 2 at a time. So that becomes 3 factorial divided by 3 minus 2 factorial. That's 3 factorial over 1 factorial, is 3 factorial, which is 3 times 2 times 1, which is 6. Now let's look at the number of combinations. Here's the formula again, n factorial over r factorial times n minus r factorial. So n factorial would be 3 factorial divided by 2 factorial times 3 minus 2 factorial. So I have 3 factorial over 2 factorial times 1 factorial. Okay, well, 1 factorial is 1, 2 factorial is 2 times 1. So I really have, I'll just write it out here in this case. Okay. Cancel the 2, cancel the 1, and end up with 3. You could also write out all the combinations and count them up, and write out all the permutations and count them up, but this is how to use the formulas. For this problem, we need to calculate both the permutations and the combinations for the following situation. Say you have 24 players and you want to make bowling teams out of them, 5 people on each team. Now if the order counts, then it's a permutation. Okay, so here was the formula. The permutations, this is n, you put the total number here, and how you're taking them goes here. So it's 24, and you're taking them 5 at a time. And the formula is 24 goes here, 24 factorial in the numerator, and the denominator is 24 minus 5 factorial. So it's 24 factorial divided by 19 factorial. Okay, you can try to work that out by doing all kind of multiplication, but you can simplify first. If you remember how to do that, that'd be 24 times 23 times 22 times 21 times 20, and then abbreviate from 19 down because it matches with the 19 factorial here. Cancel it off, and you can multiply all that together, and that gives you the number of permutations of 24 players taken 5 at a time. This is a case in which order counts. Now, if order doesn't count, then you use the formula for combinations. So 24 combinations of 24 taken 5 at a time. It starts off looking identical to the other formula. Okay, but you also divide by 5 factorial. So we know what that first part is. That will end up being, well, 24 times, let me show you how to do this one, 23, 20, 21, 20, 19 factorial. And here I have a 5 factorial and 19 factorial. I'll cancel this, but I'm still stuck with that 5 factorial. I have to divide by it. Now there's no factorials to cancel, so you just have to work it out. 24, 23, 22, 21, I forget what's going, 20, and it's divided by 5 times 4 times 3 times 2 times 1. And that will be a smaller number than for the case of permutations, but that will be your combinations. In this case, we're going to use that tree diagram. You can find some in the textbooks. It only works if you have very small numbers, of course. But let's find, we're looking for combinations, and we've got 3 restaurants and 2 movie theaters, and you want to go to, say, 1 restaurant and then 1 movie. So you will draw a line for each restaurant. So this is, I don't know, here's Denny's, here's Applebee's, and Taco Bell. Okay, then there's 2 movie theaters, and so after each one of the dinners, you can go to any 2 movie theaters. So this would be movie theater, I don't know what you want to call them, X and Y. And after going to dinner at Applebee's. You can go to X or Y movie theater, and here's your X or Y here. Now, to write out these lists, you just write out the combinations you get here. dx, dy, ax, ay. This is Taco Bell, and then go to movie theater X. So what do I have? 6. Okay. Here's a classic problem. Find the number of different license plates that can be made out of so many letters and so many numbers. In this case, 3 letters and 4 numbers. There's a question like this on the exam and also on the homework. And here, the best thing is to just think through it. And I'll show you how to do that. Okay, you have 3 letters. Well, how many choices do you have for letters? Let's say you've got 26. Although maybe they wouldn't want to use the 0, but let's say you do. So you have 26 letters to choose from here. And then for 4 numbers, single digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like 9, you could use those if you allow the 0, so that will give you 10 digits for each place. So you have, let's start choosing the letters. There's no repeats. So the first letter you can choose, how many do you have? You have 26 possible letters. Okay, you can choose one of 26. So there's 26 combinations, or 26 possible letters for the first letter. After that, how many letters can you choose? Well, you aren't going to repeat it, so you only have 25 left because you have to eliminate. Say you took the letter R. Well, you can't choose R for the next one, so you only have 25 letters to choose from. And now 24. Okay, that takes care of your letters. Here's the letter number 1. There were 26 possibilities. For letter number 2, there were 25 possibilities. And for letter number 3, there were 24 possibilities. Now we'll go to the numbers. Okay, there were 10. Okay, you could choose 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That gives you 10 to choose from here for the first number. The second number, since you can't repeat the one you already chose, 9, 8, 7. You multiply all that out. That gives you the number of license plates that can be made from 3 letters and 4 numbers if repeats of numbers or letters are not allowed. Now let's say you could repeat the letters. I just want to show you how that would work. For example, you could have a license plate that goes FFQ, say, something like that. Alright, for the first slot for the letters, you have 26 choices. Because you can repeat it, you also have 26 choices for the second letter. And you can also have 26 choices for the third letter. Now when you get down to the numbers, you can't repeat them. So as you go along, you'll have fewer and fewer to choose from.